the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who have just gone through linear combinations and the arithmetic of vectors. The next natural place we're going to go is the span of a set of vectors. And actually, this notation up here, span of V, is sort of an abusive notation. It should be the span of a set of vectors, but span of V itself is perfectly fine if you're only talking about one vector. We're going to have a span of a bunch of vectors. And you might be thinking, well, what the heck is he talking about? He hasn't even told me what span is. Well, in simple terms, the span of a set of vectors is just the set of all possible linear combinations of those vectors. And that is why you should know what a linear combination is before going into this video. And I might as well, since I'm right here, just go ahead and read the actual definition. If you have vectors v1 through v sub p in Rn, so they're vectors with n entries, then the set of all linear combinations of those vectors is denoted the span of v sub 1, v sub 2, all the way through v sub p. And by the way, that span of those vectors is a subset of Rn, and we say that that is a subset spanned or generated by those vectors. So an easy way to think about this, in my opinion, is if you have a couple simple vectors like, let's say that you have the vector 0, 1 and the vector 1, 0. Now you can actually get to any point in two-dimensional space just using these two vectors. I promise you. Just imagine if I gave you a vector, I don't know, let's call this vector AB. Then all you need to do is let c sub 2 equal A and c sub 1 equal B, and guess what? You've arrived at the vector AB. And the set of all linear combinations, in other words, no matter where we turn the dials for C1 and C2, we create a bunch of vectors, an infinite number of vectors. That infinite number of vectors is a subset of R squared in this example that I'm doing right here, that we call the set spanned by v sub 1 and v sub 2. It's a set of all vectors generated by these two vectors. It's a very nice idea and actually leads to very, very, very important theoretical concepts within linear algebra. Now, a very important note is that this means that the span of a set of vectors is a collection of all vectors of the form c sub 1 v sub 1 plus c sub 2 v sub 2 plus so on and so forth all the way to plus c sub p v sub p, with c sub 1 through c sub p being the scalar weights on those vectors v sub 1 through v sub p. More specifically, if you chose the weights to all be 0, then it's pretty easy to convince you that 0, the 0 vector that is in the span of that set of vectors. And in fact, the 0 vector is in the span of any set of vectors. So if you have the span of a single vector, let's pretend as though that vector is 1, 1, 0. The span of that single vector is the set of all linear combinations of that one vector. So basically all scalar multiples of 1, 1, 0. One such scalar multiple is 0 times 1, 1, 0. Or in other words, 0, 0, 0. So 0 is definitely an element of the span of the vector 1, 1, 0. But also, you know what else is in that set? The vector 2, 2, 0, because that's a scalar multiple of 1, 1, 0. Pi, pi, 0 is also in the span of that single vector, and so on and so forth. And this is why we say these vectors generate the span. They're like the building blocks for all the vectors that are created as linear combinations of these vectors right here. That's what the span is. Now remember, 0 definitely is a vector in every single spanning set. So if you think about a spanning set, it has to go through the 0 vector. That is, if you think about a set of vectors and geometrically what their span looks like, it will always go through the origin. So if we let V be a vector in R cubed and be a non-zero vector in R cubed, which is this blue vector right here. Tried my best to kind of highlight that vector a little bit. That'll be v. Well, any scalar multiple of that just extends or compresses or reflects v, but it still goes through the origin. So the span of v is the set of all scalar multiples of that vector v, which is a set of all points on the line in r cubed going through the vector v and the origin. So it's a very fast way to create a line in any space that you're working in. Just create the span of a single vector. On the other hand, if you're looking at a couple vectors in R cubed where they're not multiples of each other, that's kind of important, because if they're just multiples of each other, then the span of those two vectors is essentially just a scalar multiples of one of those vectors, because the other vector is already a scalar multiple. So as long as they're not multiples of each other, then the span of those two vectors is a plane in R cubed. Now this should match what I was saying earlier when I said, oh, here are some vectors in R squared, and every vector in R squared can be generated as a linear combination of those two vectors. Therefore, the span of these two vectors in R squared is actually all of R squared. It spans this entire sheet of paper, if you will. Likewise, if I have two vectors in 3 dimensions, well, their span, as long as the two vectors are not scalar multiples of each other, their span is a plane in R cubed. It's a subset of R cubed, it's a plane. So if you take a look at this picture, v is this vector right here, u is this vector right here, and 2v is just twice as long as v. You can see it right here, and 3v is 3 times as long as v, and 2u obviously is twice as long as u, and 3u, and so on and so forth. So here's one scalar multiple. Let's go right here. Here's one scalar multiple of the vectors u and v. It's 1v, it's over 1 in the v direction, and then up 1, 2, 3, 4 units in the u direction. So that vector right there, emanating from the origin and landing right there, is actually v plus 4u. And again, you can get to any vector on that plane just by taking linear combinations of u and v. Notice that plane also goes through the origin. Again, spanning sets will always include the 0 vector. So let's go ahead and tackle a computational example. Is the vector b in the span of these two vectors? Now, I just want to make sure you're paying attention. I reuse a lot of my vectors. If you take a look at this example right here, b being the vector -7, -1, 9, and the two vectors that are within the spanning set there, which I'll call for giggles a sub 1 and a sub 2, are 1, 1, 1, 2, 3, and -1, 4, 3. We have seen those before. Those vectors are actually from a previous example. Notice these are the same vectors, 1, 2, 3, -1, 4, 3, that's a1 and a2, and then b is -7, -1, 9. In this example, we were asked, can b be generated or written as a linear combination of a sub 1 and a sub 2? And we built a vector equation and found out that nope, that just wasn't possible. Hence, b cannot be in the span of those two vectors because there's no linear combination of those two vectors that will ever create b. So b is definitely not in the span of those two vectors. However, what about -7, -1, -8? All right, well, let's find out if there's a linear combination of a sub 1 and a sub 2 that can generate that new vector, which unfortunately I'm calling b. I should have called it something else, like let's call it w, just because I've already used b right up here. Well, taking a hint from a previous example, the solution set to a vector equation like this is the same as the solution set to the linear system that corresponds to the matrix whose columns are the vectors a sub 1, which is this guy right here, a sub 2, this guy right here, and then w, which again, I'm just calling that guy right there. So let's go ahead and build our augmented matrix and do some row reduction and see if there's an actual solution to this system. I'm going to go ahead and take -2 times row 1, added to row 2 to become the new row 2, and I'll also take -3 times row 1 added to row 3 to become the new row 3. You can see rows 3 and 2 are the same, so I'll just take the opposite of row 2 added to row 3. Notice that we only have pivots in the first and second columns, and there's not a pivot in the third column. That is, there's not a pivot in the rightmost column of this augmented matrix, which means that the linear system has a solution. That is, the linear system is consistent. That's from a theorem we've had in the past called the existence and uniqueness of solutions theorem for linear systems. And because there exists a solution, because again, the rightmost column does not contain a pivot, that means that this vector W is definitely generated by some linear combination of those two vectors. They didn't ask me what the linear combination is, so there's no need for me to go any further. All I need to say is yes. Of course, all my work to get there has been shown. Now, if you're working on a homework and somebody says, well, why? Then you have to say, because there's not a pivot in the rightmost column, so the underlying linear system has a solution, at least one in fact, but it could be an infinite number, but in fact, it's only one solution. Now, as a final note, before we leave this video, and actually before we leave this entire section, I want to talk about this little bit right here. The concept of span, while geometrically meaningful, is dangerous to only think of from a geometric perspective. One such danger is when you start considering the span of functions. It's very hard to even begin to understand geometrically what this means, but we will use stuff like this in linear algebra. All you need to know is what the actual definition of the span is. The span of a set of objects is just all linear combinations of those objects. So that span of e to the x and sine of x is all linear combinations of e to the x and sine of x. It's every single linear combination in the world. Specifically, it also has 0 because C1 and C2 could be 0. But it has 5 e to the x minus sine of x and a bunch of other ones. Anyhow, that's all I have for this video. Please note, span is incredibly important in linear algebra, so take your time to really digest this material. Do as many problems from the homework as you possibly can, because the span of a set of objects is not only the building blocks for some large subset, it's also the building blocks for theory in linear algebra. All right, that's it for this video. I hope you guys have a wonderful day, and please be great human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.